The actual motion of electrons around an atomic nucleus is a fascinating and intricate dance that defies our classical understanding of physics. In the early models of the atom, like those proposed by Rutherford and Bohr, electrons were imagined to orbit the nucleus in neat, circular paths, much like planets around the sun. However, these classical models quickly revealed their limitations. For instance, if electrons were truly in fixed orbits, they would continuously radiate energy due to their acceleration, spiraling into the nucleus and collapsing the atom. Clearly, something deeper was at play: interquantum mechanics, which revolutionized our understanding of atomic structure. Instead of fixed orbits, we now talk about orbitals, regions in space where there's a high probability of finding an electron. This shift from a deterministic view to a probabilistic one is crucial. Electrons exhibit wave-particle duality, meaning they can behave both like particles and waves. The behavior of electrons is described by the Schrödinger equation, which gives us a wave function denoted as psi. This wave function encapsulates all the information about an electron state. One of the most intriguing aspects of quantum mechanics is the Heisenberg uncertainty principle. It tells us that we cannot precisely know both the position and momentum of an electron at the same time. This fundamentally changes how we think about motion. We can no longer describe it in classical terms. Instead, we visualize electrons as existing in clouds around the nucleus, where the density of the cloud indicates the likelihood of finding an electron in a particular location. Now, let's dive into the shapes of these orbitals. We have s orbitals, which are spherical; p orbitals, shaped like dumbbells with 3 orientations; d orbitals, which take on more complex cloverleaf patterns; and even f orbitals, which are even more intricate. Each type of orbital corresponds to specific energy levels and angular momentum characteristics, painting a rich tapestry of electron behavior. But it doesn't stop there. The dynamic nature of electron clouds means that even within a given orbital, electrons are constantly fluctuating. They can absorb or emit photons, allowing them to jump between energy levels. This is a key aspect of how atoms interact with light and each other. When we look at molecules, the story becomes even more complex. Electrons are not confined to individual atoms. They're shared between nuclei and molecular orbitals. Here, we find bonding orbitals, where electrons stabilize the bond between atoms, and anti-bonding orbitals, where electron density can destabilize that bond. This delocalized motion of electrons is crucial for understanding phenomena like resonance in benzene or the conductivity of metals. Visualizing this electron motion can be challenging. Tools like electron density maps and probability density plots help us represent the shapes of orbitals and the distribution of electrons. But remember, these are static snapshots of a dynamic quantum state. Experimental evidence supports these concepts. Spectroscopy reveals the electronic energy levels and transitions of atoms and molecules, while techniques like scanning tunneling microscopy allow us to visualize the probability distribution of electrons at surfaces. In summary, the motion of electrons is not a straightforward path, but a complex, probabilistic phenomenon governed by the principles of quantum mechanics. Electrons exist in a state of dynamic uncertainty, their behavior shaped by quantum principles and interactions with other particles and fields. This understanding not only deepens our appreciation of the atomic world, but also opens the door to countless applications in technology and science.